Hey physics class, there is a calculation that goes along with the lab that you're doing with the letting the ice melt, and that is related to the heat transfer equation, but it's not quite the same. So let's start with a little bit of practice. If you remember our heat transfer equation, Q equals mc delta T. And just to make sure that we're all clear on this, let's do a little practice. So if you remember in my example of the lab, I was using 30 milliliters or 30 grams of water. When I froze it, of course, it became ice. And the specific heat of ice is 2.05 joules per gram degrees Celsius. And let's just say if the freezer starts out, if the temperature of the freezer is negative 15 degrees and we're just trying to thaw it out, that means that the ice will have a final temperature of 0 because it can't go past 0. If it were, it would be water. So we've got 30 grams of ice. This is the specific heat of ice. The ice starts out at negative 15 degrees. The ice ends up at 0 degrees. Go ahead and do that calculation. Pause the video here. Try and work that calculation out for yourself. And when you're ready to move on, then just resume. Okay, assuming that you've done that now, let me work it out. That would be mc delta T. In other words, it's 30 times 2.05 times 15. And calculator says that's 922.5 joules. So just to get ice, 30 grams of ice, from the freezer's negative 15 up to a melting point of 0 is going to take 922.5 joules. At this point, we've got 30 grams of water. So if room temperature is 20 degrees Celsius and this water is starting out at 0, if you do this equation again, you should be able to figure out how much energy it's going to take to bring this amount of, well, this is the amount of energy it took to get the ice up to water. Now that we're at water, how much energy is it going to take to get the water from freezing or melting all the way up to room temperature? Again, those values are 30 grams of water. Since it's water and not ice, we're dealing with a specific heat of 4.186. If you look on your chart for that. And this time, the initial temperature isn't negative 15, it's 0. The final temperature will be 20. That would be approximately room temperature. So if you didn't get this one, don't worry about it. You've got a second chance now. Try this heat transfer equation. Figure out how much energy it's going to take to warm up 30 grams of water from just having melted all the way up to room temperature. Go ahead, work that out. Pause the video, and when you're done, resume. Once again, assuming you've done that, if you substitute the values in, we're talking about mc delta T. In other words, 30 times 4.186 times 20. And the calculator says that's 2,511.6. So to sum that up, take 30 grams of ice, warm it up from the freezer's negative 15 to a melting point of 0. That's going to cost you 922.5 joules. Now you've got 30 grams of water. It just melted, and you're going to warm it up to room temperature. That's going to cost you 2511.6 joules. So together, those two means to melt 30 grams of ice from negative 15C and then heat to room temperature, which is 20 degrees C, you might expect it to take the total of those two numbers, which is 3,434.1 joules. But you'd be wrong. No, there is something else at play here, and that number is actually not sufficient. So let's see what we're missing here. So according to what's called the, here we go, the kinetic theory of matter. The kinetic theory of matter is basically the theory that all matter is made of particles that are in constant motion. And this goes along with the idea that heat, as expressed in a substance, is basically just the motion of its particles. In other words, if something heats up, hotter equals faster particles. Obviously then, colder would mean slower particles. When you're doing an equation like Q equals mc delta T, basically this equation is just describing in a macro sense how much faster or how much slower the particles are getting. However, there is a major difference when it comes to a phase change. Phase changes are different. And the reason is that if you are just talking about a liquid, a cold liquid versus a hot liquid, that's particles in the same mode of behavior, just faster or slower. But the mode of behavior of particles in a liquid is different from the mode of behavior of particles in a solid. In other words, if we're talking about in a solid, the particles are locked in place. But in a liquid, the particles are not locked in place. The particles are free. And that means that in order to get from a solid to a liquid, it's not enough just to make the particles faster. You've also got to break them apart from each other. So there is an energy quantity associated with every substance for a phase change. And when we're talking about melting ice into water, we are talking about what's called the latent heat of fusion. Fusion here refers to the locking together of particles. So when liquid water freezes, the individual water molecules basically, they get stuck to one another. I hate to use a really imprecise word like stuck, but what I mean is they can't escape each other. And that's part of what makes a solid is that the particles don't move out of the way anymore. They keep their place. So the latent heat of fusion is abbreviated capital L subscript F. And for ice melting to water, The amount is 334 joules per gram. And the way that you would figure out how much heat does it take to melt some mass of ice, I mean, if grams is in the denominator, it's pretty basic. You just have to multiply it by the mass. So the heat required to melt something is going to just be the latent heat times the mass. So how much energy is it going to take to melt 30 grams of ice? It's going to be 334 times 30. That's the latent heat of fusion for ice. That's the mass of the ice. Multiply those together. We're talking about 10,020 joules. Just back up a second. Like, remember this? That's how much energy we thought it was going to take to heat up 30 grams of ice, melt it, and then heat up that same amount, now water, to room temperature. That's barely a third of what it took just to melt the ice. So, if we were to get a sum total for this, we're talking ice, -15 to 0 degrees. That is going to cost you 922.5 joules. Now, to get from ice to water, that one is going to cost you 10,020 joules. And now we're talking water, 0 degrees to 20 degrees. That one was 2,511.6. These are the three numbers that you would need to add up to get the sum total amount of energy needed to get 30 grams of ice up to room temperature. All right, so that means we've got a new kind of problem. I'm going to demonstrate one and then assign one to you, okay? So this is the old ice cubes in a hot drink. You know how it is, you heat up water for like tea, or maybe you heat up some soup and it's just too hot, you can't eat it. So you cool it down with ice cubes. We're going to figure out what the final temperature you should expect to get if you throw ice into some sort of hot fluid. So here is the sample problem that I'm going to work out. And I'm going to assign at the end of this a problem that is similar, so you can use this example as your guide. Here's what we're going to do. We're going to have 30 grams, again, of ice that is currently at -10 degrees Celsius. And we're going to put that in 270 grams of water that is quite hot. It is at 90 degrees C. So there's a 100-degree difference between them. This is 10 degrees short of boiling. That's 10 degrees below freezing. If we put this ice in that hot water, here's what's going to happen. This hot water is going to give that ice enough energy to warm it up to 0. Then this hot water is going to give this ice enough energy to turn into water. And then this water and this melted ice, now water, are going to mix together and have a final temperature. We just have to figure out what that temperature is going to be. All right, so let's get started. First thing we need to know is, how much energy is it going to cost to get this ice up to melting? How much energy is it going to take to get the ice up to 0 degrees Celsius? Just have to put a price tag on that, an energy price tag. So we're going to be using Q equals mc delta T for that. We're looking for Q. We want to know how much energy it is. We know how much ice it is. We know the specific heat of ice, and we know how much we need to warm it up by. So let's go. The unknown amount of heat it's going to take is 30 grams times the specific heat of ice times we only need to warm it up 10 degrees. So it's 30 times 2.05 times 10. That's 615. So in order to get this ice up to the point where it could melt, it's only going to cost this hot water 615 joules. All right, well, that's not the last energy expense the hot water is going to have to make. How much energy is it going to take to melt all that ice? Well, we've already done that, but I'll do the calculation again just to be sure. The latent heat of ice, the latent heat of fusion for water, times the mass of it is going to be 334 times 30. And that was 10,020. So that one is much more expensive, energetically speaking. It's going to cost that hot water 615 joules just to get the ice up to melt. It's going to cost 10,020 joules to make the ice melt. And at this point, we've got 2 samples of water, but I don't know the temperature of this one yet. So how much energy has this thing lost so far? 10,635. 10,635 joules lost so far. What is the new temperature of this hot water after it has lost enough energy to bring negative 10 degree ice up to 0 and then melt that ice? Well, we'll keep that on hand in case I need to refer. Oh, that's not blank. Hold on. I was looking for a blank piece. Boy, I miss a whiteboard right about now. Okay, so we've lost. So we've got 270 grams of water at 90 degrees C. Loses 10,635 joules. What's the new temperature? Well, remember, we're doing Q equals mc delta T, which means I'm losing 10,635 joules. And that is equal to m c delta T. This is negative because the final temperature will be lower than 90, and this quantity will be negative. So this isn't so bad. I can just take 10,635 and divide it by both of those numbers, and I will end up with the temperature change. So, 10,635 divided by 270 and also by 4.186. Turns out it's 9.410. Well, negative sign, of course. So the temperature went down by 9.4 degrees. So if we do 90 minus 9.4, we're just doing a shortcut to solve this. 90 minus 9.410, it's actually 80.59 degrees. So just to review, we put 30 grams of ice into this hot water. Between warming the ice up to melting and then actually melting the ice, the temperature went down almost 9.5 degrees, and now the temperature is 80.59 degrees. So now we're mixing 270 grams of water at 80.59 degrees and 30 grams of water, which is currently at 0 degrees. This is the 30 grams of ice that just melted, and this is the 270 grams of water that just cooled down to 80.59. Okay, let's do that calculation. In this particular case, this is where the heat lost must equal the heat gained. This one's losing energy, this one's gaining it. So let me go ahead and put this one on the left with the negative sign so everything works out. I've got M C delta T equals M C delta T. I think I might have gone off frame there. Sorry, there we go. So this is MC delta T, mass of the melted ice. It's water now. Final temperature is unknown, but I know it started at 0 because it just melted. This is M for the hot water, C because it's water, and delta T. They end up at the same temperature because they're mixed together, but this one started at 80.59. And I can't forget to have a negative sign over there. Okay, well, just a whole bunch of math now. However, I can save myself a little bit of work because there's a 4.186 on both sides. I'll just cancel that out. Oh yeah, and I cleverly set this up so this would be simple. So this is 30, that's 270. If I divide both sides by 30, that reduces to 9, and that cancels out. So I've got negative TF minus 0 equals, and that's 9 times the temperature change. Well, that's nice. I've got another line here where I could fit this, so let me just go ahead and remove that parentheses. Negative TF equals, distribute this 9 times that temperature minus, and now 9 times 80.59. I've got that here. Here we go. 725.31. All right, well, I am almost out of room here. I'm going to scoot that up. Sorry to make some of the notes disappear. So I can just subtract 9 TF from both sides, end up with minus 10 times the final temperature equals negative 725.31. So those negative signs cancel out, and I can just divide by 10, which means I have a final temperature of 72.531 degrees. There you go. Okay, one more slide and then your problem. One more slide, one more, I don't know what to call these. One more board. B-O-R-E-D. Here we go. So we are clear. When you are calculating heat transfer with a phase change, you've got the energy cost to heat up to the freezing point, but the freezing point is also known as the melting point. See, freezing or melting, it just depends what direction you're coming to it from. So if you're starting below freezing, you need to heat up to the point where it can melt. Then you need to calculate the energy cost to actually melt the stuff. Remember, that would be the latent heat of fusion times the mass. And then finally, the energy cost to whatever the final temperature is. Energy cost to equilibrium. So I did the problem in which 30 grams of ice at -10 degrees were put into 270 grams of water at 90 degrees. Whew. Here it is. Here's your assignment. Please find the final temperature of 50 grams of ice that starts out at 15 below into, this time we've got a bowl of soup, so it's going to be a bit larger, 450 grams of water. However, this isn't like terrible soup. This is just a little too hot, and we've got it at 75 degrees. Okay, so this number, this number, this number, this number, they're the only things different between this and the example that I just worked through. Yeah, best of luck on that. My recommendation would be that you work this out by hand and that you send a picture to me so that I can see your work. If you ask me a question, I'm going to ask you what part of this the question is in. Are you having trouble getting the ice to warm up to the point where it can melt? Are you having trouble figuring out how much energy it takes to get the ice to melt? Or are you having trouble figuring out what the final temperature is now that the mixture is hot soup and cold water? All right, well, that'll do it for this time. Yep.